Moving backwards now into chapter 5, we had looked at chapter 6 already, right, which dealt with the right triangle trig, and then we moved into the um, sketching of the angles in standard position where we had the x, the y, and the r. So we're now going to go backwards into chapter 5, which actually deals with what's called the unit circle approach to trig functions. And this is actually an easier version of what we just did in 6.3, where we were looking at the x, y, and the r, because now what's going to happen is we're going to show that our r is really just going to be 1, which makes things easier. So first off, what is the unit circle? Right? These are our objectives for this section. Unit circle, terminal points, and then the reference number, which is going to be very similar to the reference angle that we had dealt with in the chapter 6. So the unit circle. So the unit circle is just the circle that's centered at the origin and has a radius of 1. Okay? And the equation of that unit circle is going to be x squared plus y squared equals 1. And that shouldn't really be surprising considering what we had in chapter 6, right? In chapter 6, we had done these angles, right? And we had showed that if this point was xy, this distance here we called x, this distance here we called y, and we had called that r. But now r is not even that difficult anymore, right? R is always just going to be 1 because the radius is 1, so it makes things much simpler. So in the other chapter, we had the relationship x squared plus y squared equals r squared, but now we know r is fixed at 1. So now we know by Pythagorean theorem x squared plus y squared equals 1. So it's actually even simpler than what we had been looking at earlier, which is nice. Okay, so there's the equation of the unit circle again, x squared plus y squared equals 1. So one thing that we can do is we can show that specific points lie on the unit circle. So how do you do that? It's just like doing a check, right? So you're realizing that this point here is your x coordinate. So you replace x with square root of 3 over 3, and you realize that this is your y coordinate. So you replace y with radical 6 over 3, and make sure that when you square each and then add them together, right, the sum of the squares of those things are 1. Right? So you end up with 3 ninths plus 6 ninths equals 1, and it does check out. So what are some terminal points on the unit circle? Suppose t is any real number, right? If t is greater than or equal to 0, what you're going to do is you're going to travel along the unit circle counterclockwise, right? Because it's positive, so this is no different than what we've been doing, where you say a positive angle is rotated counterclockwise, starting at the point 1, 0 and moving in a counterclockwise direction. And if t is less than 0, you're going to start at the point 1, 0, and you're going to rotate around the unit circle in a clockwise direction. Okay? So in this case, t is some positive value because I rotated counterclockwise, and in this case, t is some negative value because I rotated clockwise. So what happens? You arrive at a point on the unit circle, which will be called the terminal point, determined by the real number t, right? So you think of really t, the easier way to think about this is t is really the angle, right? Yes, it's the distance along the circumference of the unit circle, but you really want to think of t as being the angle. So any angle will give you a point on the unit circle. All right, so we had talked about this. Since the circumference of the unit circle is 2 pi, if you start out at 1, 0 and you move counterclockwise all the way around the circle back to 1, 0, you've traveled one complete circumference, and one complete circumference would be 2 pi. So if you want to go halfway around the unit circle, you're only going pi, right? You're going from 1, 0 to negative 1, 0, right? So if you go pi units, you've gone halfway around the circle, so you'd end up at the point negative 1, 0, right? So pi would correspond to the point negative 1, 0. Okay, and then they show you some of these quadrantal angles here that we had talked about earlier, right? When you travel pi over 2, you've traveled a quarter of the circle, and that gives you, so when t is pi over 2, the point on the unit circle is 0, 1. So pi over 2 corresponds to 0, 1. We had just said this before, right? Pi corresponds to negative 1, 0. Here you've gone 3/4 around the circle, right? Which is going to be 3 pi over 2. So when t is 3 pi over 2, you've arrived at the point 0, negative 1. And then, of course, if you go all the way around the circle where t is 2 pi, you get back to the point 1, 0. And this, again, ties into the whole idea of coterminal angles, right? 0 and 2 pi are coterminal because they give you the same terminal point, all right? So those are the quadrantal angles and the points that correspond to them. So 3 pi, right? This is where you want to, again, think of the idea of coterminal angles. 3 pi would actually be the same as coterminal with pi. So 3 pi is going to be coterminal with pi. Negative pi is coterminal with pi. And negative pi over 2, right? 2 pi is really 4 pi over 2. So this is going to be coterminal with 3 pi over 2, right? So 3 pi, you can see, yes, to get 3 pi, technically what I would do is I would wrap around one complete rotation and then a half of another rotation. But as we said, it's the same as pi, right? It's coterminal with pi. Negative pi, okay, I wrapped around the circle a half a rotation, but I went clockwise, would be the same as if I did counterclockwise half the circle, right? Which would also be pi. So 3 pi and negative pi are both coterminal with pi, right? So they're always the same point. So these two, A and B, would actually have the same terminal point, which would have been negative 1, 0. And then negative pi over 2, which you can think of as a quarter rotation clockwise, is the same as 3/4 of a rotation counterclockwise, which would have been 3 pi over 2, which corresponds to the terminal point 0, negative 1. Right? So negative pi over 2 is coterminal with 3 pi over 2. Right? And that's what we just determined there. So again, the key here is different values of t can determine the same terminal point, right? And what are specific examples of that? 0, 2 pi, 4 pi, 6 pi, so on and so forth, are all coterminal. And they're all also coterminal with negative 2 pi, negative 4 pi, negative 6 pi, so on. These are all coterminal. They all have the same terminal point, which in this case is 1, 0, right? 0, 2 pi, 4 pi, 6 pi, so on, and negative 2 pi, negative 4 pi, negative 6 pi, and so on, all have that same terminal point. All right, so pi over 4, right? So pi over 4 is actually half of pi over 2, right? So it's halfway between 0 and pi over 2 along the unit circle. And if you remember, pi over 4 is really like a 45-degree angle. So what we had in this situation is this was one of those special triangles, right, where we had both of these things we had called 1, and we had called this the square root of 2. Now the problem with doing that now is we know the radius, or the hypotenuse in this case, right, is not the square root of 2, but the hypotenuse, or the radius, is really 1 in this case. So we know that x and y are the same, so we know x squared plus x squared has to be 1. So in other words, 2x squared has to be 1. So x squared has to be a half. So x is really 1 over the square root of 2. But as we've seen a couple times already now, 1 over the square root of 2, if we rationalize, becomes square root of 2 over 2. So what is this point here? This point is square root of 2 over 2, comma, square root of 2 over 2. Right? And how do we know that x and y are equal? Because we knew it was a 45, 45, 90 right triangle that we were creating there. So that's how that works out. We're then told that similar methods can be used to find the terminal points determined by pi over 6 and pi over 3, which again, this is our other triangle, right? So we used our special 45, 45, 90 triangle to find the terminal point determined by pi over 4. We could use our 30, 60, 90 triangle to determine the terminal point defined by pi over 6 and pi over 3. All right, we just used our 30, 60, 90 triangle. So then there's what you get, right? So then they show you the different values, right? So 0 we knew was the point 1, 0. Pi over 4 we knew was the point radical 2 over 2, radical 2 over 2. But then, pi over 2 we knew was 0, 1, right? That was straight up. But then the other ones that you would get from the 30, 60, 90 would be pi over 6 and pi over 3, right? Because pi over 6 is really like 30 degrees. Pi over 3 is really like 60 degrees. So those are the points that you get from that. So then what you can do is, if they now give us, let's say, negative pi over 4 or 3 pi over 4 or negative 5 pi over 6, we can use these values and just realize, hey, well, where is negative pi over 4, right? Well, negative pi over 4, all negative pi over 4 is, it's pi over 4, except it went clockwise. So negative pi over 4 would actually be that. And what is this point x comma y? Well, it's the same as pi over 4, except y is negative, right? So at negative pi over 4, x is still square root of 2 over 2, but y is now negative square root of 2 over 2, right? So to do this one, we would just say it's going to be square root of 2 over 2, comma, negative square root of 2 over 2, right? Because this is in the fourth quadrant, and in the fourth quadrant, x is positive, y is negative. Okay, and then we do a similar thing with 3 pi over 4. So 3 pi over 4 would actually be, now this is pi over 4, so 3 pi over 4 would be here. So 3 pi over 4 would have actually been this, which again is similar to pi over 4. It's the same height, right? So y is the square root of 2 over 2, but x is now negative, right? So when you're at 3 pi over 4, you're in the second quadrant, but you're really at the same point defined by pi over 4, except, values might be negative. So the x is negative, so it's negative square root of 2 over 2, but y is positive, so it's square root of 2 over 2. And then when you do negative 5 pi over 6, that one's a little trickier, right? So negative 5 pi over 6, let's erase some of this stuff here. We're tracing clockwise to there, right? Again, if you're not sure, negative 5 pi over 6, you can think of it as degrees. It's negative 150 degrees. So this would be your negative. So you are in quadrant 3, right? You're in quadrant 3 where both x and y are negative. So it's going to be similar to pi over 6. It's going to be a similar point to pi over 6, except both x and y are going to be negative, right? So it's not radical 3 over 2, 1/2. It's negative radical 3 over 2, negative 1/2, right? Because pi over 6 and negative 5 pi over 6 are actually just opposites, right? Both x and y become negative. So if I was going to do that one would have been negative radical 3 over 2, negative 1/2. And again, why? Because this is in the third quadrant. Right? So the idea of saying what quadrant it's in, it just determines what's positive and what's negative, right? So in the fourth quadrant, x was positive, y was negative. In the second quadrant, x was negative, y was positive, but then in the third quadrant, they were both negative. And then I just had to determine what was my reference angle, right? So so for the first two, the reference angle was pi over 4, and then for the last one, the reference angle was pi over 6.